other professor teaching this class. I look a bit young, but I promise I'm a legitimate professor. I'm not just pretending. Today, we're going to switch gears a little bit, but before we have to get through some logistical announcements before we get to the fun stuff. So first announcement, homework 1 is out. It's been released and it's due Monday at midnight. And so again, for homework 1, much like with every other homework, you can look on edX, you can use the autograder, you can submit as many times as you'd like, and check your score until you get to the score that you're happy with. Next, we have projects, right? So project 1 has also been released. Project 1 is due Friday at 5 p.m. Again, why 5 p.m.? Because we're trying to make sure that you have some sort of semblance of a Friday night. So 5 p.m., project 1. And what we wanted to share with you about project 1 is that you need to start early because it's longer. It takes longer to do than most of the other projects in the course. Definitely much longer than project 0. So don't take project 0 as a baseline and say, oh, everything's going to take about as much. So start early and ask questions and use Piazza. And what I'd like to ask you to also do is to talk to each other on Piazza and answer each other's questions, right? So we're a community, we're trying to learn together, so we have to help each other out. And then finally, the midterm date. The midterm date has finally been set, and it happens on Tuesday, March 15 from 7 to 10 p.m. Any questions about logistics? All right, now to the fun stuff. So in this fourth lecture, we're talking about constraint satisfaction problems. And to give you an idea of where we are in the class and how that relates to the things that we've talked about so far, in the previous 2 lectures, Peter has shared with you all about search problems, right? Remember search? What were algorithms that we could use to solve search problems? Who will volunteer some algorithms? I'll call on you if you don't raise your hand. There we go, thank you. A-star search. Okay, A-star search was probably the fanciest of search algorithms, right? Because it used the cost to go and the heuristic. What were simpler versions? Yeah. Breadth first search, depth first search. All right. So Peter has told you all about those algorithms. Today we're going to start talking about a slightly different topic, which is called constraint satisfaction problems. Now, what I want to point out is that actually has a lot to do with search as well. That's why these topics go one next to the other. It will turn out that constraint satisfaction problems are actually going to be a particular type of search problems. So then you might wonder, okay, well, if we know how to solve search problems, why are we talking about constraint satisfaction problems, which are just a type of search problem? Well, it will turn out that because we can actually define them as a particular type of search problem, they'll have more structure than generic black box search problems. And what we'll be able to do in these next 2 lectures is actually take advantage of that structure, leverage that to create algorithms that solve these constraint satisfaction problems that are generic to constraint satisfaction problems, but that actually leverage that structure to be more efficient than naive search algorithms would be, like breadth first search, like depth first search, and so on. So that's kind of the plan. We're going to spend 2 lectures talking about what these problems are and how to efficiently solve them. And we'll see that they appear a lot in real life as well. So they're an important special case. Good. So I figured I'd actually start with an example. Who wants to venture an answer to what a constraint satisfaction problem might be? It doesn't have to be a mathematical answer. It can just be an intuitive answer. When you hear constraint satisfaction problem, what comes to mind? Yeah?
Like you have some limitations, and then you have to solve the problem within rules like that.
Right, so you're going to have some sort of limitations, and you have to make sure that you meet those limitations, those constraints, when you solve the problem. Now, a running example through these 2 lectures is going to be some particular constraint satisfaction problem that's called map coloring. So here's what happens with map coloring. With map coloring, we get our little robot, and we hand our robot a map, like this one here. And the map has all these different regions, okay? So what we tell our robot to do is color the map. Pick colors for each region, but make sure that no 2 adjacent regions end up having the same color. Why might that be a thing that we want to do when we color maps? Why is it important that two adjacent regions don't have the same color?
Neighboring countries are different colors that come apart.
Exactly, so that you can tell them apart. Because if I colored this guy here and this guy here with the same color, then when I look at the map, I might not realize that there's two different regions. I might think that it's one big contiguous region, right? So that's what map coloring is. That's the example. It's going to be a running example in these two lectures. And I want to point out that even though it sounds a bit silly, because how often do we color maps? It turns out it's a good representation for a lot of real-world problems outside of actually coloring maps. So for instance, if you have some kind of scheduling task, so you're trying to get tasks and you're trying to schedule them in some sort of schedule, but tasks depend on resources. What you want to do is to figure out when these tasks should all run, but you want to make sure that if two tasks run at the same time, these would be sort of say adjacent tasks, if two tasks run at the same time, they don't share the same resource. They don't rely on the same resource. So tasks that rely on the same resource are adjacent tasks, and we don't want to color them with the same color, meaning we don't want to put the same time on them. Okay? So that's an example of a constraint satisfaction problems that appear a lot in the real world. Now, in general, constraint satisfaction problems have a few ingredients. So one of the ingredients is that they have variables. Okay? So in this case, what are the variables for map coloring? Someone said color, someone said, any other guesses? A bit louder? Country is right. So the different regions, this is x1, this is x2, are our variables. And they're variables because we don't know what to do with them, right? We don't know what colors to assign to them. And then we have these domains for each of these variables. And in this case, the domains are what? Colors. Well, not more colors, because the variables are the regions, and the domains are possible colors that we could assign to each region, right? So for x1, we could do red, green, blue. For x2, we could do red, green, blue, and so on. And then we have this handbook here, the map coloring handbook, and that defines the constraints. That basically tells us, look, if I have x1 and x2, they can't both have the same color. That's what the constraints handbook tells us. Okay, so those are the ingredients of a constraint satisfaction problem. You have variables, you have domains, you have constraints. And my claim is that you can think of these as search problems. So to think of them as search problems, in search we have states, we had a goal test, and we had a successor function. What could be the states, the goal test, and the successor function for a constraint satisfaction problem? How might you formulate this problem in terms of states, goal test, and successor function? Yes?
Maybe the initial state could be like a graph that points edges between adjacent regions.
Okay, so we can think of some sort of a representation where these variables are all kind of, we represent them by a graph, and we have edges between adjacent regions, and we start to think of how to color that graph. All right, but when we talk about when we talk about search, we want to do search on graphs, right? So we have to think of sort of how do we take this geometry of the problem and turn it into, okay, these are the states, then these are going to be the successors, such that the goal is going to be a fully colored such graph. Yeah?
The states can be every color configuration of the map, and then the successor function is just flipping one of the colors.
That's a good idea. So the suggestion was maybe all combinations of assignments, those are the states, and two assignments are next to each other, they have an edge between them, if they only flip one of the variables to one value, right? And then we have a goal test that says, okay, for this assignment, does that meet all the constraints? So that's one way of looking at it. On the slide, we have a slightly different answer. We can just, yeah, did you want to venture a different answer?
Is the states like literally the variables and
an assignment, right? So you have x1 and you assign it red. And that could be a state, or in his answer, you have to look at all of them. You have to say x1 is red, x2 is green, x4 is whatever it is, and you look through all of them, and they each have a color, and that's a state. And you can go from that state in your search tree to a next state by just flipping one of those variables. So that was the answer. Yes?
Could we look at it as like coloring in the countries one at a time, and then the successor function would be coloring in the next one, and then the search terminates if we can't color in something that would fail the constraints, and then the go test is everything's colored in the constraints.
Bingo, very good. So that's actually the answer that we had. Your answer is also okay. You can think of doing search like that, and this is going to be a slightly different formulation of that she suggested. You could do either, and there's some trade-offs, some advantages and disadvantages. So you can think of states as partial assignments. So the second answer there said, well, states are going to be full assignments. We're going to make sure to specify what x1 should be, what x2 should be, what x3 should be, and so on until we get to xn, and that's a state. And the new answer, what we're looking at is maybe we can have a partial assignment. Maybe a state is just x1 is red and x2 is green, and I don't know what happens to the rest of them. They're not assigned yet. Okay? So we can think of states like that. Then we have a goal test, which now the goal test can't just check if all the constraints are met. It also has to check whether the assignment is a complete full assignment, right? So you don't just look at, because x1 is green and x2 is red, you don't just say, okay, we're good because this satisfies all constraints. You actually have to instantiate, assign all the variables, and then check constraints. So that's going to be our goal test. And then finally, we have a successor function. And the successor function is basically going to do the following. It's going to take a partial assignment and assign one more variable to any new variable that's not yet assigned to any new value. And those are going to be the successors. So if we look at this formulation, what is our initial state? Where do we start from? Yes? All the variables are unassigned. Nothing is assigned yet. And then we go to one variable being assigned, then we go to two variables being assigned, and so on. Okay? So you can think of constraint satisfaction problems as a search problem, and you can run search algorithms on them, and we'll see how well that works. Good. So let's step back a moment. Since these are search problems, let's think back to what we use search for. We use search for problems that meet a few requirements. First of all, we were talking about a single agent making decisions. We were talking about coordinating with other agents and so on. We were in a fully observed state space. In other words, the agent knew where in the graph it is. The agent knew what state it was on. It could tell, right? And then we had these deterministic actions, meaning when I'm in a state as an agent and I take an action, I know exactly with 100% probability what state I'm going to end up in next. So we had deterministic actions, and we had a discrete state space. So the state space wasn't continuous. These were actually just nodes in the graph. And within constraint satisfaction problems fit this, and the types of problems that we've seen before fit that, and there's a subtle difference between them. So with the type of constraint satisfaction, with the type of search problems that we've seen before, we mainly looked at planning problems. So planning problems required us to come up with a sequence of actions to get to the goal, right? We knew what the goals were, but we didn't know how to get there. And we had to figure out how to traverse the graph and find a path, a sequence of actions that will take us to one of the goal states. So the path was really important. That's what we were searching for. We didn't know how to get there. We're searching for a sequence of actions to take us there. And paths had various costs, right? You could get to the goal in one way or in another way via different costs. And we found these paths at different depths in the search tree. And then we had heuristics, right? Like in A-star search, we had heuristics that were domain-specific that gives us guidance on how to actually solve these problems. And planning problems are great. Constraint satisfaction problems are subtly different. Constraint satisfaction problems come up in this different type of search problems that we call identification problems. And in identification problems, the goal is the important part. It doesn't matter what sequence of actions you take to get to the goal. What you care about is finding a goal that meets the constraints, right? Finding a goal state. And that's the important part. So you can think of this as sort of the difference between these two cartoons. On the planning side, we have our ninja robot who's trying to steal the gem. Okay? And the robot knows where the gem is, but it doesn't know what sequence of actions to take in order to get to a goal state of having stolen the gem. So we're searching and searching for actions that get this ninja robot to get to the gem. On the bottom side, with identification problems like constraint satisfaction problems, we have this detective robot, and the detective robot is trying to find the stolen gem. And in a sense, once you've found the stolen gem, you don't know where it is, but once you find it, it doesn't really matter where you looked, because you can find it again, now you know where it is. So in identification problems, the goal is important. In planning problems, the sequence of actions that you take to a goal is important. And in identification problems, unlike paths having various costs, in identification problems, you'll see that all paths have the same depth. What depth do all paths have? Thinking of constraint satisfaction problems and thinking of the way we just formulated them as search problems. What depth do all paths in a constraint satisfaction problem have in the search tree? Yeah. N, where N is the number of variables, right? Why is that? Well, because you start off with an empty assignment, and then you take one action to assign one variable, you take another action to assign the second one, and so on and so forth, and you only get to a goal when you've actually assigned all of N variables. Okay? So all paths will be at the same depth. Good. So that's the difference between the kinds of problems that Peter has talked about so far and the kinds of problems that we're looking at now. Stepping even further, constraint satisfaction problems have more structure than standard generic search problems, right? So with standard generic search problems, we were given states, but they were these black boxes. They could be anything. We didn't know necessarily what they were. They could be strings. They could be anything. We had a goal test. And the goal test could be any function. All we needed it to do is we needed to be able to give it a possible state, and we needed the goal test to decide whether it's a goal state or not. So you can think of the goal test in a generic search problem as this little judge here. And what the judge does is you hand it over a possible state, and the judge declares, no, it's not a goal, or yes, it's a goal. And you can't go into that judge's brain and figure out how it makes that decision. All you're given is access to this judge, right? And then the successor function could also be anything, any black box. And notice that constraint satisfaction problems are different from that. Because constraint satisfaction problems have, we actually know what's in these black boxes. We can actually peek through them. So for instance, with states, we actually know that states are partial assignments of variables. And that's important. We'll leverage that. And then the goal test, well, the goal test is you no longer have to rely on this judge, right? Because the goal test basically says, is this assignment complete? And are all constraints satisfied? And we're given this handbook that specifies the constraints. So we can actually peek through the handbook and figure out what the judge will say. We don't have to go to the judge and get an answer and be surprised or not surprised by it. We can actually figure out whether a goal state will be, what a state will be a goal state or not. And we'll actually use that quite a bit. So this specification of a goal state through constraints is a simple example of what we'll call a formal representation language. And this is what we're going to use to be able to come up with algorithms that are going to perform better than naive search algorithms, generic search algorithms like depth first search, breadth first search, and so on. We'll take advantage of that. Good. So that's kind of the story, the big story with CSPs. Now let's look through some examples. We've already seen map coloring. We're going to look through a few more examples. And what I want you to get out of these examples is not just the fact that there are many CSPs out there and they're formulated in different ways. But what I want you to get out of that is to start thinking of when you see a problem in the world, how would you actually formulate it as a search problem or as a constraint satisfaction problem? Because the thing is that once you'll have taken this class, if you have the specification of a problem as a constraint satisfaction problem, you'll have all the tools to go out and solve it. That's not the hard part. The hard part is you'll see a problem in the real world, and you won't know necessarily whether it's a constraint satisfaction problem or not, and you won't know how to turn it into an actual specification that your algorithms can deal with. What are the variables? What are the domains? What are the constraints? Right? So we're going to go through these little exercises where we're going to figure out, okay, if we have this kind of problem, what are these entities? How do we define it as a constraint satisfaction problems? And just remember that. In AI in general, you go out into the real world, and the hard thing and the interesting, fascinating thing that we all also do research on is take a real world problem and actually formulate it as a problem that you actually know how to solve. So we've seen map coloring, right? So with map coloring, just to recap, we had these variables that were all the possible regions. So in this example, we have Australia. I'm not super familiar with Australia geography, so you have to forgive me if I butcher some of these. But we have Western Australia, Northern Territory, Southern Australia. We have Queensland here, New South Wales, Victoria, and Tasmania. And those are the regions in Australia, and those are going to be our variables. Next, we have domains. Like we said before, these domains are possible colors, right? So we're going to think that of the possible colors we want to assign to these variables, and in this simple example, they're going to be red, green, or blue. Those are the domains. And then finally, we have constraints. So the constraint was adjacent regions must have different colors, okay? So now you can think of how to actually specify this in math or in code, right? Because I can't just tell my computer or my robot adjacent regions must have different colors. I have to actually specify them somehow. So it turns out that there's two different ways you can think of specifying constraints. One way is to specify them implicitly. Implicit specifications of constraints basically say, write a snippet of code or write an equation that you can evaluate to see if that constraint is satisfied or not. So an example of that is going to be that the assignment of Western Australia has to be different, not equal, to the assignment of Northern Territory. That's an implicit constraint. But you can also specify constraints explicitly. Does anyone have an idea of how that might work? What might be an explicit specification of the same constraint? Yeah.
Would it be that Western Australia is said to be one color, and then the Northern Territory is another color, and then we have them?
Right, we look at the tuples, right, and we actually define all possible values that the tuple can take that are allowed according to the constraint. So in this example, we look at Western Australia and Northern Territory as a tuple, and we say, well, that tuple could be red, green, red, blue, and so on. What are we going to miss from that set? What are the tuples that are missing from the set? The tuples that use the same color, right? So we won't see red, red, we won't see green, green, and so on in that, but we'll see all the ones that have different colors. And that's an explicit representation of the constraint. So that's how you can represent constraints, and then solutions are assignment that satisfy all the constraints. And the picture up there on the right, this guy shows, I think, a solution to this constraint satisfaction problem. Because no two adjacent regions have the same color. Yes?
So for this problem, do you just assume that you start with the knowledge of how many colors you need and how many states you have?
You assume that you know the state, assume that you know the variables exactly. So you know the regions and you know where they are, right? And you assume that, yes, you've given enough colors. If you haven't been given enough colors, let's say that we were just given red and green, what would we need to do? We would need to basically return something that says, I cannot solve this. This is not solvable. Okay? And that's also an answer. It might be interesting in some cases to figure out whether a CSP is solvable or not. All right. So that's map coloring. Now, some of you already hinted at this. It makes sense to associate with such a constraint satisfaction problem something like a graph. We'll call these constraint graphs. They don't specify the full constraint satisfaction problem. But what they do is they specify the nodes. All the different variables are nodes. So Western Australia is a node, North Territory is a node. And then if they're adjacent, if there's a constraint between them, then they have an edge. So Tasmania, for instance, that's alone there. It's not connected to anything. And that's because there's no constraint involving Tasmania, because Tasmania is an island and is not adjacent to anything. OK, so that's what a constraint graph looks like. And in binary CSPs, binary here is a little bit misleading. Binary CSPs means that each constraint relates to variables. That's what the binary comes from. It doesn't talk about the domains being 0, 1 or anything like that. Binary CSPs are CSPs where the constraints relate at most to variables. So in a binary constraint graph, nodes are variables and the arcs, the edges, show the constraint. And we'll see that when these constraint graphs are going to be pretty useful in that they tell you something about the structure of the problem. In that case, for instance, they tell you that Tasmania is its own separate problem. And so you don't have to mix it with other ones when you solve the CSP. And that's something we're going to come to next lecture. So those are constraints graphs. Keep that in mind. We're going to be using them at some point. Another example, so that was map coloring. Now, how many of you have heard of a puzzle called N queens? Nice, quite a few. So with N queens, the idea is you're given a chessboard, and the chessboard is N by N. Okay, and then you're given N queens, and your job is to put the queens on the chessboard such that the queens don't attack each other. And if you know anything about chess, you know that when queens attack each other in a few cases, they attack each other when they're on the same row, they attack each other when they're on the same column, and they attack each other when they're also diagonally related, when they're on the same diagonal. So that's when queens attack each other. And the idea with this puzzle is place these queens, you have N queens in this N by N chessboard so that you have no queens attack each other and we have this nice and peaceful kingdom here. So, good. So we're going to look at two formulations for this. Because, like we said before, it's not trivial to think of how to take a puzzle like that and figure out how to formulate it as a CSP. So we need to get a bit of practice with that. So we're going to look at two formulations. The first formulation, our variables are going to be all the positions, all the cells on the board. So xij, where I goes from 1 to n, and j goes from 1 to n. I is the row, j is the column. That's what we're going to look at as variables. Now, can you guess what the domain will be for these variables?
There's a queen there or there's not.
Sorry, a bit louder.
There's a queen there or there's
Is a queen there or is it not? So the domain is going to be 0 or 1. 0 means there's no queen on that spot. 1 means there's a queen. Good. Now, all we're missing is the constraints. What are the constraints? Yeah.
No queens on the same rows, columns, or diagonals.
No queens on the same rows, columns, or diagonals. How do we write that? Well, for instance, we could write it in this way. We can say that we can write this explicit definition where we enumerate the possible tuples that are allowed. So for instance, we could look at all i's, j's, and k's between 1 and n, and we can say for xij and xik, so these are two positions that share the I index, which means they're two positions that are on the same row. Okay? So for all positions that are on the same row, we're going to allow the tuples to be 0, 0, 0, 1, or 1, 0. Notice that the only one missing is 1, 1, because what does 1, 1 mean? Right, it means that there's two queens there and they're on the same row, and that's bad, right? So in this explicit definition of the constraint, we're enumerating all possible tuples that are allowed. Of course, we have more constraints, right? Because we have to look at the rows as well. We have to look at the diagonals as well. Is this enough? Let's say we looked at rows, columns, and diagonals. Is that all we need? are solutions to this problem what we're looking for if we solve this as a constraint satisfaction problem? Sorry, what? Right, there should be n queens on the board, right? Because right now, you can assign all these to all be 0. Notice that 0, 0 is okay everywhere. And it's in the domain of everything, so you could just say everything's 0. But everything's 0, what does everything 0 mean? There are no queens there, so that's bad. That doesn't quite meet our puzzle, right? So we have this other constraint that says, okay, the number of things that are 1 has to sum to exactly n, because we want exactly n queens on the board. So that's one way to formulate this puzzle as a constraint satisfaction problem. That's formulation 1. Now we're going to switch over to a different formulation, formulation 2. So with formulation 2, what we're going to do is we're going to have the variables be all the different rows, Q1, Q2, Q3, all the way up to Qn. Those are going to be the variables. And now the domains are going to be 1, 2, 3, all the way up to n. Why does that make sense? Why can't we get away with so many fewer variables? Only n instead of n squared. Yeah?
Because we're building in the constraints into the space, so the variables already assume there's only going to be 1 queen on each row.
That's right. We're building in some domain knowledge here. We know that we can't put 2 queens on the same row, right? So we might as well not even allow that in the problem definition itself. We can define each variable to be a row, and we just say that there's 1 queen on every row, and it can be in 1 or 2 or 3 or slot n, but there's only 1 of them. And now the constraints for this, basically you have to think of how to write the constraints that basically say that somehow the queen in row 1 and the queen in row 2 can't be threatening each other. So you could do that explicitly too, where you say, okay, for the queen in row 1 and the queen in row 2, that tuple can be 1, 3, 1, 4, 1, 5, and so on. Why is 1, 1 missing? Because they'll be in the same column. Why is 1, 2 missing as a tuple? Because they'll be on the diagonal and they're threatening each other, right? So you can define explicitly like that. So that's the second formulation. Notice that formulation 1 has many more variables, okay, and it has more constraints. Now, on the other hand, the domain is much simpler in formulation 1. So there's a little bit of a trade-off there. But basically what we managed to do with formulation 2 is we baked in some things that we know about the real world to then simplify our job when we actually try to solve the problem. And that's an important thing to keep in mind. All right, that was n queens. Here's another example. How many of you know about cryptarithmetic? Many fewer. I didn't know about cryptarithmetic either, but apparently cryptarithmetic is a thing. And it's especially useful for little robot detectives, I guess, investigators, I don't know. But the idea with this little puzzle is that you're gonna get these words and you're gonna have some mathematical operation between them, like addition or multiplication, and you have to figure out what they mean. In other words, you have to figure out what number each letter stands for. And you have to do it in a way that when you plug in a number for each letter and then you do the addition or multiplication or whatever you're doing, it actually all adds up. It's all consistent. So what are our variables here? Yeah? You can do the letters and the carry digit. Perfect. So obviously we're going to have variables, the letters, because those are the things where we don't know what we should assign them, right? But it turns out that to be able to track all of the constraints, we need to make sure that we're also keeping track of the carry digits. So the domains are going to be just the numbers from 0 through 9, and then we're going to have constraints. One constraint, and that's a constraint that the cryptarithmetic gods told me about, which is that all of these things have to be different from each other. Okay, but then the actual constraints that talk about how the addition has to work out nicely are going to look something like that. So for instance, this constraint says, okay, look at this column has to make sense. So that means that if you look at O plus O, you have to be able to get R And you might have this carry digit x1 over here that you also have factor out. And you move on through this chain like that. So those are the constraints. And then you can think of this as a constraint graph representation for this problem as well. But the challenge here is that you have these constraints that don't talk about just two variables anymore. Because what did we do in constraint graphs? Where we took two nodes and we put an edge between them if there's this constraint that relates them. But now our constraints don't just relate two things, they relate many things. In this case, for instance, they relate 4 variables. So for instance, this constraint here talks about that constraint representation there. And what we're doing here is we're still having the variables as nodes, but then we're adding additional nodes in this graph. They're going to look like squares instead of circles. And we're going to put an edge between this new node that represents the constraint and all the variables that it touches on, all the variables that it involves. Okay, so for instance, with this one, this square here stands for this constraint, and it involves O, it involves R, and it involves the carry bit x1. That's the constraint graph representation for this. And we'll get to constraint graphs later. This one here talks about how all the things should be different, and so on. Good, so next up, one more example, Sudoku. So with Sudoku, this is what happens. How many of you know Sudoku? Do I need to explain Sudoku? Oh, okay, good. Mostly everyone knows Sudoku. So my mom is just crazy about this one. So with Sudoku, what we have is each of these cells that are empty, those are the variables, and then the constraints are going to be these can be 1, 2, 3, all the way up to n. Those are the domains. And then for the constraints, we have all these all diff constraints, because we have a 9-way all diff for each column, a 9-way all diff for each row, and a 9-way all diff for each region, each of the 9 regions. So that's how you can think of Sudoku as a constraint satisfaction problem that some of us enjoy solving all the time. So those were some examples of taking these puzzles and turning them into constraint satisfaction problems. Now, it's worth also talking about the high-level picture, what kinds of constraint satisfaction problems are out there. So far, we've mainly looked at discrete constraint satisfaction problems. That means that all the variables have these discrete domains. And we've also mainly looked in the particular case of discrete variables for constraint satisfaction problems that have finite domains. So we had these variables that only had d possible values. So in map coloring, we were looking at red, green, or blue. Those were 3 values, and so on. So now, as the slide already says, otherwise I would have asked you, having d possible values for each variable means that essentially we're looking at an order of d to the n possible assignments to these variables. So that's kind of the space. Out of those assignments, we have to find one that works. And I want to point out that this is hard. And the way you can tell this is hard is that Boolean satisfiability, for those of you who know what Boolean satisfiability is, Boolean satisfiability, which we know is NP-complete, is an instantiation of a discrete finite domain constraint satisfaction problems. So it's not trivial to solve these. And then, of course, they can have infinite domains, and you can also start thinking of continuous variables. We're not going to touch on continuous variables in this lecture, but I encourage you to take either CS 170 or maybe something on the E side on optimization and constraint optimization. You'll get to find out a bit more about what to do when these variables have continuous domains. Now, so those were kind of how you can break up CSPs. You can also think of how to break up constraints. So we talked a bit about this already. You have unary constraints, and unary constraints involve a single variable. So unary constraints are kind of boring because they just say stuff like, okay, you can't assign green to South Australia. And what do you do when you can't assign green to South Australia? When you define the CSP, is there something you can do that makes the problem much easier and you don't have to deal with that constraint at all?
You start with that problem. You start with South Australia and you do the other two.
So So you can imagine of structuring the order of the variables somehow, because now South Australia has more constraint. We'll actually get to that. But when you have unary constraints, things are actually much easier than that. Because since you never have to consider green as a variable for South Australia, the easiest thing to do is just remove it from that variable's domain. And never even consider assigning green to South Australia, because you know that's not going to go well for one of these constraints, namely the South Australia has to be different from green. So unary constraints, they're just equivalent to reducing the domains for these variables, and that's okay. Binary constraints involve pairs. And then we can talk about having higher order constraints that involve 3 or more variables. These are often called n-ary constraints. And an example of that we've seen with cryptarithmetic, where our constraints involved more than 2 things. They involved the O and the R and the carry bit, for instance. So that's an example there. And now I also want to point out that there's this thing called soft constraints. They also appear a lot in real life. So what soft constraints mean is, okay, I don't need this to be a hard constraint, meaning it's not absolutely imperative that this is true. And if it's not true, I don't even want to know about it. They're more like preferences, these soft constraints. They're more like, okay, well, if you have the choice, I prefer that you use more red than more green, right? So they're not, it doesn't mean that you can never use green. It just means that you should try to use it ideally less than you use red. So we're gonna put these kind of on the stack and get back to them later on in the class. Good, so those are varieties of constraints, and let's also talk about this, that these happen in the real world a lot. So all of you have had experience to a certain extent with the first 2, right? Scheduling classes, assignment problems, and timetabling problems, thinking of who teaches what class, and which class is offered when and where in the schedule. And one other one that I wanted to mention, this is particularly dear to my heart because I've actually, when I was your age, back in the day, yeah, long time ago, when I was an undergraduate, I did a research internship after my first year, and I worked in transportation scheduling. I was working for this institute in Germany, and because it's Germany, stuff actually runs on time. Okay, so their problem was, all right, I have my buses and I have my trains like BART and so on, and I need to make sure that when people come to the station with BART, they can actually switch to the bus. The bus hasn't just left a minute ago. So we had all these constraints, and we were trying to find assignments of variables to satisfy them, and that's kind of one idea on transportation scheduling. It's a constraint satisfaction problem as well. So they appear all over the place. There are many real-world problems that involve that. So now let's take a 2-minute break and come back and talk about how to actually solve these. All right, let's get started again. So now we know what CSPs are, how to formulate them, and so on. Now let's talk about how to actually solve them. So what happens when someone stole the gem and the robot detective is trying to find it? How do you actually do that? And we've already gone through the starter search formulation, right? But just to recap, we have states, and they're defined by partial assignments of variables. And then successor functions just say, look at this partial assignment, pick a variable that hasn't been assigned yet, pick any value and assign it to that variable, and that makes a successor. And then a goal test looks at the current assignment and says, well, is this a full assignment? Is it complete? And if it's a full assignment, does it actually satisfy all the constraints? So we'll start with a straightforward search approach and then go ahead and improve that. So let's go back to the Australia example of map coloring. What does breadth first search do when you run it on this problem? Yeah.
So it starts somewhere and assigns it to some color, and then it assigns all the nearby territories to a color, tries to at least, and then I guess it would go layer by layer and try to assign additional colors until that fails.
So that's a good guess, but that sounds more like depth first search in this case. And here's why. You start off with an assignment that's empty assignment, and then you look at all the successors. What are the successors? Well, they're Western Australia can be green, Western Australia can be red. What are other successors? Right, so you can go to Northern Territory could be green, Northern Territory could be red, and so on. Those are all the successors. What does breadth first search do? We'll actually go and visit everything, right, before it goes on to the next step. Is the goal, is any of these states a goal? No. Any of these states? No. Where is the goal? All the way at the very bottom of the tree. This is the very definition of the breadth first search nightmare. Okay? So if breadth first search were a person, it would stay up at night worrying that these things might happen to it. All right? So this is just the absolute worst, because what you're going to do is you're going to go through all the search tree, everything, until you finally find the goal. It's the worst possible case, pretty much. So breadth first search, not so good. Depth first search, much better idea in this case. Because you know that everything is at the bottom, so you might as well try to get to the bottom and then backtrack from there and do stuff at the bottom, instead of building up everything and then looking at the bottom. Okay, so let's see how depth first search actually does on this problem. Here's a graph. It's a simple graph. And we're going to run this algorithm that is called naive search here and actually runs depth first search. So we're going to start with the empty assignment like here. And then we're going to take one of the successors. Let's say that we break ties in favor of this node and we break ties in favor of blue. So we assign that blue. Now, next, what do? We call the successor of that node. Successor function on that node, and it has successors, and the first successor is, let's say, the next node, and what color? Someone said red, but in the beginning we broke ties for blue, so if we're consistent in the way we're breaking ties, we're going to get blue again. What happens now? You think, you realize that you failed and you backtrack, right? Wrong. Because what happens is breadth first search checks if this is a goal. It's not a goal. Then it calls it successors. And who has successor? This guy does. What is the successor? Blue, the next node with blue. And it goes on and on and on and on. And it assigns blue. And then it gets to here. This one is not a goal state. It doesn't have successors, so it backtracks. And then it tries something else. Try something else. Try something else. Nope, that doesn't work. And I'm going to make this go faster and faster. Essentially, it backtracks, it backtracks, it backtracks. And all this work is totally wasted, right? Because what did it make its first mistake? Like a millisecond in, right? It made its first mistake here. And you think, well, it should have known. But the thing is, how could it know? Because if you just think about it as a generic search problem and you think of, well, was the successor function was the goal test, that's what depth first search does. So what we should talk about is, well, how to actually try to fix these issues and kind of, when we get ourselves into bad solutions, backtrack earlier. Yes?
The successor function, by definition, only gives balance things. Wouldn't that go against the constraints automatically, which goes against the successor function?
That's a great idea, and that's something we're going to be talking about. All right. So, depth first search has some issues. And the fact that it doesn't detect failures early is an issue, and there's actually another issue. So we're going to fix that into something called backtracking search. So backtracking search takes advantage of two ideas. The first idea is actually pretty simple, is that it doesn't matter what order, orderings are commutative, and so you can fix an ordering and decide on that. So instead of when you call the successor function, it gives you Western Australia can be all of these things. And you also, instead of assigning Western Australia, you can assign Northern Territory to any of these things, which is what the successor function does now. You can instead just fix the ordering. So you can say, well, on the first layer, I have Western Australia, then I have Northern Territory, and so on and so forth. So that's the first idea. The second idea is to actually check constraints as you go. So only consider values that do not actually conflict with the previous assignments. And you might have to do some computation to do that, right? Because this is not a goal test. This is not your typical goal test. Basically, you want more than that. You want something that says, this does have, it's not a goal, it does have successors, but I can already tell that whatever you try to do with the rest, this is not going to work out because constraints are already broken. So we're basically talking about this kind of incremental goal test that we're going to be using, and we can do that because we actually have access to the constraints. If we only had access to a little judge that says, yes, it's a goal, no, it's not a goal, then we'd be in trouble. So depth first search, with these two ideas, is called backtracking search. And you might think, well, doesn't depth first search backtrack already? Yes, yes it does. We don't necessarily name these things in the best way, but it's called backtracking search. That's what it's called in the literature. We're going to stick to that. So backtracking search. And we're going to use this reference in the future. With something like backtracking search, you can solve n queens for n equals 25. Let's keep that in mind. We're going to come back to that. So here's an example. With backtracking search, you start with the empty assignment. Then you move on, and you have all of these possible things, and they're all OK. But then when you pick this guy here, and you call for its successors, you're not going to consider assignments that are already conflicting with the previous ones. And in particular here, if you assign Northern Territory, because that's your next variable, you're never going to consider an assignment where Northern Territory is also red. So that's what backtracking search does. It uses a sort of incremental goal test, so to say. And let's see how backtracking actually performs back in this graph. So what we're going to do is going to go here and switch from naive search to backtracking. OK, so we start off, we assign, let me reset. We start off, we assign blue. And depth first search would have gone and assigned blue next. But now we actually know that this is not going to be consistent, and we're going to assign it red. So we pretty much skipped all of that search going on where you assign this blue and that blue, and then you keep on trying to fix everything else, until finally you realize, OK, assigning the second one to be blue was a pretty bad thing to do. So that's nice. And then it goes on, it goes on, it goes on. Will it backtrack? Or is this enough? Is doing backtracking search, so to say, is doing depth first search with these two ideas enough to just go straight to the goal and never have to backtrack? No, it can get itself in trouble too, right? So here it assigns green, but there's nothing else you can do, so it backtracks. I'm going to let this play. And I'm going to make it a little bit faster. And bam, solution. Okay, so note that that was much better than that. Let's look at that just for fun. Let's look at that again. So here's naive search. All right, all right. So we're going to play this. Let's play it at 10x. Yeah, that's even better. Let's play it at 10x. This is what depth first search does. It's glorious. Okay? Now let's reset. Backtracking, also at 10x. Done. These two ideas, very simple, but they can actually save quite a lot. So that's backtracking. Now, here's the pseudocode for backtracking search, and we're not going to go through it in detail, but you have it in your slide for reference. The things to note is you start off with an empty assignment. Okay? Start off with an empty assignment, and then you pick one variable to assign, and you have this ordering that tells you which variable to pick. Now, we haven't talked about what this ordering should be, but for now, we can imagine that you just pick a random ordering as long as you stick to it throughout the algorithm. So you pick the next variable that hasn't been assigned from your ordering, and then you look at the values that it has, and you have some ordering for the values in its domain, and you pick one of them, and then you check if it's actually consistent with the assignment so far. That's backtracking. Now, it turns out that you can do more, because backtracking obviously still backtracks, right? So like we discovered, it might still get itself into troubles and have to backtrack and so on and so forth. So we're going to be looking over a little bit today and next time at 3 different ideas, fairly simple ideas again, but that will tremendously improve even upon backtracking. So these ideas are going to be ordering. Ordering is something we've basically already hinted at, because what did backtracking search do? Well, it had an ordering, and it took the first variable to assign from that ordering, and then it took the next variable, and so on. And so obviously you might think maybe it actually matters what variable ordering we pick, right? For some problems, one ordering is going to be better. For other problems, another ordering is going to be better. So we're going to be discussing how to order these variables, and also how to order their values. So that's going to be the idea with ordering. Before we get to ordering, we're going to talk about filtering. And the idea with filtering is, all right, we're already doing a fairly okay job at detecting that we're going to fail clearly because we just assigned 2 blues and that's never going to work. But can we do more? Can we look further into the future and detect these inevitable failures earlier so that we don't have to do a bunch of work and then backtrack? And then we're going to talk about exploiting structure in these constraint graphs. So those are going to be the 3 ideas for improving backtracking. We're going to start with filtering today, and filtering is about keeping track of the domains of the unassigned variables and starting to cross off bad options. So that's what filtering is about. And a first type of filtering, the simplest thing you can do is something called forward checking. So filtering just says, I'm going to keep track of the domain of the variables that I haven't assigned yet, and I'm going to remove things from it. But the way you do that is not yet defined. With forward checking, you have a simple thing that you can do, which is cross off values that violate a constraint when added to the existing assignment. Okay, so whenever you make an assignment, you also cross off values that in the future are going to get you in trouble from the domains of those variables. So here's an example. Again, our favorite map coloring example. So we start off, and let's say that we assign red to Western Australia like we usually do. What happens now? Well, we made that assignment. We can actually go through the domains of the other variables that are not assigned yet and remove red from them if they actually have a constraint with Western Australia. So in particular, we're going to look at Northern Territory. Northern Territory sits here. That's adjacent to Western Australia, and we're going to remove red. Why? Because if we had red there, we would never be able to assign it anyway because it conflicts with the assignment we just made. Good. And we're going to do the same for Southern Australia, which is the only other region that is adjacent to Western Australia. So far, so good. Now, we're going to go forward, and let's say that our ordering says that we should go all the way over here. This is Queensland. It's, let's say we made it green. If we made Queensland green, then again, we go through NT, SA, and New South Wales and remove green from there. So that's what we did. We went through NT, removed green, New South Wales, removed green, Southern Australia, removed green. Now we go forward. Let's say we pick that guy, we assign it blue. We assign this blue. We remove blue from here. We already know that we should backtrack. We already know that we've made a mistake. Because by assigning here blue, what happened is that Southern Australia, which was neighboring basically all of these different assignments that we made, this guy over here, now can't be anything. We've removed all values from his domain. We're in trouble. So we already know that we failed, and so we can backtrack. So let's look at the demo of what happens when you actually add this forward checking. So what you see here is that now we actually have all these nodes, but we keep track of the possible domains that they have, and we're going to keep on removing values from that. So we start off first, we assign blue, our favorite thing, and note that as soon as we assign blue, all these other ones know that they can't be blue anymore. Now we move on to the next one, we assign red. The moment we do that, we know that its neighbors that are unassigned, they can't be red anymore. Then we move on, and here we get to green. We realize, that eliminates this guy, so we have to backtrack. So backtrack a bit. And then we're good. And that's what forward checking does. It keeps track of the domains of the remaining variables, and whenever we make an assignment, we eliminate things that we know we're not going to be able to assign to them anyway. Good. So does forward checking need to backtrack? We've already seen it backtrack, yes. Why? Why is the forward checking not enough to just ensure that we can keep assigning things and we'll never have to backtrack and we'll reach the goal? Any ideas? Yeah.
There might be a situation where the first ones you assign are valid, but then you end up hitting a dead end.
Yeah, so you keep eliminating these things, but you only look one step ahead. So what can happen is you get up in this particular situation here. So let's say that we're here. We've assigned Western Australia to red. We've assigned Queensland to green. We've done forward checking, so we know that we should have eliminated red and green from NT and red and green from SA. But that puts us in a little bit of trouble, right? Because now what we're going to do is maybe eventually we're going to assign blue to one of these, but in the meantime we might pick V or NSW or whatever. Eventually we're going to get to SA, we're going to assign blue, and then we're going to be in trouble on NT, right? And we didn't detect this with forward checking. At this point in forward checking, everything is still fine. Forward checking things, okay, we're in good shape. But in a sense, we've already failed because there's nothing we can do with the rest of the variables that will enable us to be consistent. And forward checking doesn't detect that because it only looks one step ahead. It doesn't actually reason about the implication of that to then the rest of the constraints. And that's the key here. What we can do is go from simple forward checking to something called constraint propagation. And in constraint propagation, we're actually going to be, propagating these changes forward. All right, so that's what constraint propagation is. It will reason from constraint to constraint. And we're going to spend the next 11 minutes of lecture on that, and then we'll be done. So talking about constraint propagation requires us to introduce a slightly new idea here. So I want you to bear with me for this. Okay, I know it's the end of lecture, but we have to focus on this constraint propagation stuff. So we're going to introduce an idea that's called an arc. So an arc is going to be a directed edge from one variable to another. And you might say, wait, what, directed edges? We looked at the constraint graph. It didn't have directed edges. It just had normal edges. Where does the direction come from? Arcs are a new idea that we're introducing now. And arcs can go from x to y or from y to x. We'll use both directions. But we're going to say when an arc goes from x to y, we're going to call x the tail and y the head. Does that make sense? Because it goes from x to y, so y is forward, that's the head. X is in the back, that's the tail. So x to y is an arc, and it's got to be consistent if for everything that I can choose in its tail, for every x that I can choose, then there's some y, there exists at least a y for which, in the head, for which I could assign that y, and I wouldn't violate the constraint. So let's look at some examples. Here's an arc. It goes from NT to WA. Is this arc consistent? Well, let's check. What does it mean for it to be consistent? NT is the tail, WA is the head. We need that for every x in the tail, there's something in the head that we can assign. So let's say blue. If I assign NT to blue, is there something I can assign in WA that's consistent? Yes, because I can assign, in fact, I have to assign red, but there's red, that's okay, blue is okay. What about green? Because it has to happen for every x in the tail. So in the tail I have blue, red, and green now. For blue, we're okay. For green, are we okay? Yes, good. Are we okay for red? No. So this arc is not consistent. What about this arc? Is this arc consistent? No, for the same reason. Okay, so what we're going to do is, the idea here is that we're going to go through all possible arcs and we're going to make them consistent. And the way we make them consistent is by deleting values from the tail that cause us to go into trouble. Like here we would delete red, here we would delete red. And the way to remember this, and this is important, is you can think of this mnemonic of, I'm driving and constraint satisfaction police pulls me over. Okay? So constraint satisfaction police pulls me over. What are they going to do? They're going to check my trunk. They're going to check my trunk, which is the tail, and they're going to remove things from the trunk that are causing trouble. All right? We remove from the tail, delete from the tail. Remember that. We delete from the tail, delete from the trunk. All right. So can we think of, if now we have an algorithm where we look at all arcs or some arcs, and we remove things from the tail of these arcs that get us in trouble, can we say that forward checking is a particular way of doing this? How is forward checking connected to checking consistencies of arcs? What did we do in forward checking? We assign a variable. Oh, there we go. We have an answer.
Well, isn't what we're doing now forcing us to only evaluate our neighbors sequentially instead of jumping around and hoping that we're okay?
So what we did, okay. So far we've introduced the idea of, okay, we can have arcs, we can define arcs, and we can check that they're consistent. With forward checking, what we were doing is, whenever we made an assignment, what did we do? We looked at all variables that have constraints with that new variable that we assigned, and we made sure that everything's okay, right? So what arcs were we looking at when we were looking at forward checking? Yes?
The arcs are the same color, right? Or they were adjacent also?
Right. We were looking at all neighbors of that assignment that we made, all the variables that were adjacent, neighboring. We were looking at the arcs from that variable to the assignment that we made. So we looked at the assignment that we made as being the head, all the other things as being the tail, and we checked all arcs that go from the tail, from these new variables, to the head, the variable that we just assigned. And we remove things from these new variables domains They were the tail, so we delete from the tail. We delete it from the tail whenever that variable would cause us in trouble with our current assignment. So forward checking is enforcing consistency of arcs pointing to each new assignment. That's what we're doing with forward checking. So it's a special type of this, but we can also think of moving forward beyond just forward checking, beyond just looking at the neighbors and deleting from the tail, to then say, well, what happens now that I just deleted the stuff? Does that affect other constraints, right? And propagate that. That's the idea of constraint propagation. Propagate that through the chain. And so we can think of enforcing arc consistency, not just of these particular arcs that go into the new assignment that we're making, but of all of the constraint satisfaction problem. Arc consistency of an entire CSP. So let's look at an example of what can happen in this case. Let's look at this arc. Let's say that this is our current state. We deleted some stuff from the domains. We've made some assignments. In particular, we assigned WA and Q. And now we're at this situation here, and we're looking at the arc from V to NSW. Is this arc consistent? Who thinks yes? Okay. Who thinks no? Okay. Someone who said no. Can you explain to the rest of the class why you might think that what particular domain value of V is causing trouble? Well, let's see. If we assign blue, can we assign something in NSW that's okay? Yeah, we can assign red. If we assign green here, can we assign something in NSW that's okay? Yeah, we can assign either blue or red. If we assign red, can we assign something in NSW that's okay? Yeah, so this arc is actually consistent. Remember this arc, we're gonna come back to it. Now, let's say we go from SA to NSW as an arc. Is this arc consistent? Yes, because if we assign blue, we can assign red here, and we're good. Now, let's look at this arc the other way. Is this arc consistent? No. What's the problem? Where does it hurt? What's the value that's bad? The blue. We have to get rid of the blue, because if we assign blue, then we'd be in trouble. We can't assign anything in SA that's consistent. So we're getting rid of the blue. Good. Now let's go back to our first arc. It went from V to NSW, and it was consistent. Is it still consistent? No, it's not consistent, because now we eliminated blue. We can only assign red. So if we actually pick red here, then we'd be in trouble. We actually have to delete red from that to make it consistent. So note what happened. And we can go forward and forward. Note what happened. When we remove the value to enforce consistency of some arc, we got in trouble with an arc that we previously declared as consistent. So that means it's not enough to visit every arc once and make it consistent to make sure that at the end, all of the arcs in the CSP are going to be consistent. So we actually have to loop over this, and whenever we make a change, we have to revisit arcs that are affected by that. That's going to be important. So the nice thing about arc consistency, it detects failure much earlier than forward checking if you actually enforce it. It can be run either before you start everything or after each assignment. And here's the last question for you. What is the disadvantage of arc consistency? Why might you not want to do it? That's exactly right. It's much cheaper to do forward checking than it is to do arc consistency. But arc consistency can buy us a lot. We'll see that in the demo, and we'll look at the Sudoku next time. Thank you.